Good morning. Today we will discuss about the second theorem, the Thevenin's theorem. In the last lecture, we have done numerical problems on superposition theorem. I hope that you are well acquainted with the superposition theorem. In today's class, we will discuss Thevenin's theorem. I hope that by the end of this lecture, you will be able to describe the steps that are involved in determining Thevenin's equivalent of a given circuit. Okay. So I'll start with the statement of Thevenin's theorem and then I'll give the explanation. And at the end of the lecture, we will solve a simple problem on Thevenin's theorem. So before I start, let me give you a simple introduction to Thevenin's theorem. Thevenin's theorem is an analytical method which is used to change a very complex circuit into a simple equivalent circuit consisting of a single resistance with a source voltage. So let us suppose there is a very complex network. Now let us suppose there is some sort of load resistance. This is your circuit. So this RL is going to vary every time. Now let us suppose this is the simple problem. RL is varying every time. When RL is varying every time, we need to analyze the entire circuit again and again whenever RL is going to vary. So it consumes us more time if we keep on solving the entire problem again and again and again. The best way is nothing but this part is completely unchanged, right? So why don't we simplify this part to a simple circuit which will be represented by a simple voltage source and a resistance. Then in this case, if this entire network is represented in this format, then it will be easier for us, because if you want to determine the current in this case, what I can do, I can directly write it as, so every time if RL varies, I can determine the current in this network rather than doing this entire problem all the time again and again and again. So Thevenin's theorem states that this entire network, which consists of so many elements, etc., it can be represented by a single voltage source in series with a resistance. And there is a condition that this network which you are trying to simplify, it must be a linear bilateral network. Okay. So the statement states that any linear bilateral network consisting of any number of elements or any number of sources, it can be replaced by a single voltage source in series with a resistance. Now what is the value of resistance and what is the value of VTH? Because so many resistances are being now simplified into RTH. So many sources are being simplified into VTH. So what is the value of RTH and VTH? So this is the statement. Thevenin's theorem states that any two-terminal linear and bilateral network or circuit having multiple independent and dependent sources, it can be represented in a simplified equivalent circuit. We call it as Thevenin's equivalent circuit, which consists of a single voltage source in resistance with in series with a resistance. And the value of the voltage source, we call it as a Thevenin's voltage. It is equal to the open circuit voltage across the terminals. While that of the resistance, we call it as a Thevenin's resistance. It is equal to the equivalent resistance seen from the open circuited terminals. So VTH, I'll write it here again for you. VTH is open circuit voltage, whereas RTH is equivalent resistance. Both are to be measured at the terminals. So your entire network now will be represented by a VTH and an RTH. Okay. So with this is the Thevenin's equivalent circuit. So any network which consists of several EMFs and resistances, etc. Now this network is being replaced by a VTH and an RTH. Okay. So what is the procedure for determining the Thevenin's equivalent of the network? The first and foremost step what you are supposed to do is nothing but you first remove the elements where we are supposed to find the response. Okay. So once you remove the elements, the terminals will be open. The second thing is you are supposed to determine VTH. So find the voltage across the open circuited terminals. Because you have already open circuited it. Second step is determine the VTH or V open circuit. We call it as Thevenin's voltage. The third step is you remove all the independent sources. You replace them with their internal resistances. Okay. Remove sources. And then you determine equivalent resistance. After removing sources only, you should determine the equivalent resistance. So find the equivalent resistance across the open circuited terminals. Okay, this we call it as Thevenin's resistance. And finally, you draw the Thevenin's equivalent circuits. How? A VTH in series with your RTH. And from here, you can calculate the response in the load resistance. Okay. So this is the Thevenin's network, the steps involved in Thevenin's network. The first thing is open circuit the terminals. The second thing is determine VTH. Third thing, replace the sources. Fourth one, determine RTH. And finally, you keep VTH in series with RTH. So these 5 are the steps which are involved in determining the Thevenin's equivalent circuits. So now we'll try to solve a problem on Thevenin's theorem. Okay. See, find Vx by first finding VTH and RTH to the left of AB in the figure which is given below. So this is your Vx. So we need to determine the VTH and also RTH in this given network. So first of all, the first step is we should remove the element, right? So in this network, so this is my network, right? So this is my resistance. So I am removing this resistance, and see, these are my open circuited terminals. Whatever the 2 ohms resistor is there, I have removed it, and these are my open circuited terminals. Now the step 2 is you should determine the Thevenin's voltage. So step 2 is to determine the Thevenin's voltage across this open circuited terminals. I am drawing the open circuits again. This is 4 ohms, 6 ohms, 12 ohms and 30 ohms, right? This is the open circuit. So I am applying nodal analysis here. This is A, this is B. So I am taking it as 0 volts. This will also be 0. This is 30 volts. I don't know this one here. This is going to be V. Okay. So there is only one effective node. If I apply KCL, 3 paths are there. This is V1 minus 30 by 12. V1 minus 0 by 6. And this is open circuit. So I don't get any current here. So if I solve this, my effective voltage here is 10 volts. Now, what is my VTH? VTH is equal to VA minus VB, right? So since no current flows here, the same 10 volts will be appearing here. Here also it will be 0 volts. 10 minus 0, it is 10 volts. Now, step 3, I should replace all my sources with internal resistances. Now I already removed this one. Now there is one source. Now voltage sources will be short circuited, whereas current sources will be open circuited, unless there is any internal resistance mentioned. So what I'm doing is I'm just shorting this one. So if I short this one, what I will be getting? 1, 2, this is shorted, this is 4. So 1, 2, this is shorted and this is 4. This is your step number 3. And step number 4 is determining the equivalent resistance. Now if you carefully see, these two are in C. Always try to remember. Assume that the current is flowing here and it should leave here. So the current is being divided into 2 parts. Again, it is coming back, it is joining here and it's going like this. So what I should do now, these two are parallel paths because this is across this terminal, this is also across the same terminal. So 12 and 6 are in parallel. So if 12 and 6 are in parallel, what I will be getting? I will be getting 12 into 6 by 12 plus 6. Right. So it is 4 ohms. So what I will be getting? Here 4 is already there. Here in place of these two, I will be getting 4 ohms. Right. So what I will be getting here? 4 plus 4, the equivalent resistance is now, both are in series. Same current is flowing. So 8 ohms is the equivalent resistance. So step 4 is determining the Thevenin's equivalent. And finally, what I will be doing now, I will be drawing the equivalent circuits. What is the equivalent circuit? The Thevenin's voltage, which I have got it as 10 volts, in series with your Thevenin's resistance, 8 ohms. Right? So 10 volts in series with the 8 ohms. Now what I have done, I have just kept my load resistance, the initial one which I have replaced here. It is 2 ohms. Now this is your circuit. If I want to determine the total current in the circuit, what is the way? What is the total voltage? 10. By what is the total resistance? 8 plus 2. So 10 by 8 plus 2, it is 1 amp. If you want to determine the voltage across this one, since 1 ampere current is flowing, 1 into 2, it is 2 volts. If I want to determine the power loss, it is V into I. So it is 2 into 1, it is 2 watts. Like this you can calculate. Okay. So I hope that now you are able to describe the steps. Once again, a quick review. The first one, open circuit the terminals. Number 2, determine VTH. Third one, replace the sources. Fourth one, determine RTH. And fifth one is draw the Thevenin's equivalent circuits. Okay. So try to practice this problem at home and we'll solve more problems in the class tomorrow.